Online should be almost 25, 30 people. 40, that's too much.
Or maybe the combine, I don't know. Yeah, but yeah, there's a total of 23.
So, alamak. Okay. Now, last week we looked at the structure of the eye, and I asked you to put a few, maybe just one star, all right, at this particular thing. This thing here. I don't really need you to memorize the entire eye structure. We are, after all, not doing a course in looking at the physiology of the eye. The physiology of the eye is really to, to let us understand later on, right, how we humans perceive visual information, and thus how our behavior, all right, can begin. So a quick one will be what? There are three mechanisms, let's put it this way, there are three mechanisms that we can actually see color. Last week, before the lecture ended, we were talking about one of the mechanisms. Now, a quick one. So this mechanism requires certain specialized cells in your retina. And what are they called? The general name? Cone cells, yes. So cone cells comes in three types. What are the three color types? Recap now. What are the three color types? Red, blue, green. Not red, blue, and yellow. Not. All right? So sometimes people wonder, why is it that in primary school we learn that when we put dyes together, the primary colors are red, blue, yellow, but then when we look at light, it's red, blue, green. This has to do with the way your brain interprets information. All right? Anyway, in the last 15 years, there are some research showing that we may actually have a fourth primary color, which is yellow. Okay? But then they cannot, it's not conclusive yet because they cannot decipher whether it is, at least the researchers, they still cannot, it's all very tiny, it's all very difficult to check. We always need better instruments for this. But apparently, in your retina, it's definitely this red, green, and blue. But then your optic nerve doesn't just reach all the way back to your occipital lobe. There's about 90% of the information from your optic nerve that will go to occipital lobe, which will actually put together all the red, green, and blue information. Okay? But apparently, there is actually a yellow, a special nerve that transmits yellow color. All right, so this reaches the midbrain as well as the occipital lobe. So there's going to be more research plus a lot of argument before they finally come to a consensus whether whatever we learn in primary school, secondary school, right, all the basics, whether it should be revamped, or maybe this is just an extra thing, like it's a transition of basic to secondary kind of color coding. The secondary is easy, you know the rainbow colors, right? All the mixture of colors, they are there. So the final verdict is not in yet. So I suppose you just, if you are interested, you just track it maybe 10, 20 years down the road. It wouldn't be so soon that they will have a consensus, all right? Now, so let's stick to it, as in stick to the three color cells, red, green, and blue. So it is and all these things are only found in which part of the eye? These cone cells? The macula or the fovea area. So that will be the spot where the light, all right, focused on. So remember, light will pass through your lens and focus on the spot somewhere in the retina. So at a very, very tiny spot there, it's like the bullseye, that's where you find out the cone cells. You will not find cone cells in other parts of the retina. So despite having 100 million all these optic cells in your retina, you find that because all the cone cells are located in a tiny spot in one place, so out of the 100, only 7 million are cone cells. Okay? Now, I'm not going to run through this. I need you to recap on your own. What are the features, all right, comparing between cones and rod cells. All right, we covered that last week. Now, so with this information, we now have some idea of how humans can perceive the world. We are able to see colors because we are able to detect the specific light energy. The color that you see is just a way your brain tells you what kind of light energy you are receiving. All right, if you're a machine, then it will register in the form of waves. All right, whether it's white waves or very compressed waves. Now, so that's one mechanism. Today we're going to run through the other two. I asked you to, oh, where did I? No, that's okay. I think I can still, the board is still fine. I'll just move the board. What? Go. Something wrong with the online thing? I'll switch to that slide first, then yeah, I'm at the slide when you project, I'll continue. Online people, are you looking at the wrongly colored American flag? No? I think then we need to, oh, you need to project, as in you need to share screen to, yeah. No, this is, they are actually seeing this screen, I think. What are you all looking at now online?
I'm looking at this.
Then they should be seeing that, right? Are you seeing the flag or are you seeing a lot of your classmates?
Flag.
Flag, okay, great. Then we just continue. Now, last week I asked you to go home and try this, right? Now, you notice that, those of you who tried, right? You notice that when you stare at this wrongly colored flag for about 30 to 60 seconds, then you look at a white spot, the real American flag comes out, right? Why? How come? Now, actually, the way the eye works, right, there is a way to short circuit it. In other words, when we are trying to understand perception, we realize that there are flaws in our perception. Therefore, our behavior may be misguided. So that's what we are actually trying to understand. So let's look at how our ability to perceive things can be short-circuited. Now, if I go back to this okay, we are now back at this. I want to use this to, remember I mentioned that these ganglion cells are like the so-called the first level of brain cells, right? They process information. But what is happening is, if you look at this, there is this pink color cell here, all right? Now, and then there are the green color cells. Now, I don't need you to memorize them, all right? I only need this picture to explain how it works, and then that's it. So what happens is, when your cone cells get activated, they pass the information to the first level of processing cells. But the connection is not direct, as usual. All right, and in your nervous system, there are a lot of intermediate connections, so that there can be variations. That's why it can account for all your almost infinite number of behaviors, right? So same thing here, it has evolved to have a bridge. This is the green color cells, something called the visual bipolar cells. Now, when the information passes through here, right, the thing is, it's always arranged such that there is a modulator, that means this regulator here. This is like the customs officer. It will decide how much information to pass through. But This pink color thing is always arranged where it has arms in opposite kind of cone cells. What I mean by opposites? What I mean is something technically known as complementary colors. So for example, right, red color, if you can go home and do this, if you put bright red color and bright blue color together, you find that it's like very glaring, especially somewhere in the middle. So if I were to have red color here and a blue color I put side by side, you find it's very glaring, like something in the middle was like, it's like white, but it's not really white color, right? So colors, before they look at all these biological stuff, right, they thought that, oh, colors have opposite colors. And it's not red versus blue. It's like, there's what? There's red versus green. And then there's what? There's, is it yellow and blue? So that's red and green, and I think, yeah, yellow's opposite is actually blue, something like that. All right, now we're not going to look at colorology. Of course, there's no such word, okay? Now, but doesn't matter. All right, what I'm trying to highlight is that colors have something opposites. Later on, they realized that why are there opposites is because when we evolve, the opposite kind of, to be able to tell contrast very well, right, you need to evolve the pink color cells and they grip on to opposite things so that when the signal comes, right, they will tell you that, wow, these are very contrasting colors and they are weird. They should not happen in nature. And literally, you find that in nature, right, except for nowadays we have artificial lighting. But in nature, you hardly will find something that is very bright red and then very bright blue or bright green together. If it is, it's usually dangerous. For example, you look at some of the patterns on poisonous plants and poisonous insects. They have this kind of very strange contrasting colors. So we evolve the pink color cells to actually grip onto the thing and modulate the signals so that it can tell you that opposite colors, you better be careful. But then here is where we can short circuit it. When they are in opposites, right, what is happening is a lot of people thought that the eye works in a way where, when there's light coming in, then it will start to function. Actually, it doesn't work this way. What happened is your cone cells and your rod cells are actually firing all the time. Yeah. So it's just like thinking. You can tell yourself, calm down, don't think, but you will still think, right? There's only one kind of people who successfully learn how not to think in this world. They're called dead people. So your nervous system is functioning all the time. Even when you sleep, there's some kind of activity, just that you're not aware of it. So the eye is always firing, but when the light signal hits the cone cells, it actually stops it from working. So this break in signal is actually a trigger, and then this trigger will then be passed on. So that's why you need the bipolar cells. It will then start to act up. You say, hey, wait, suddenly no signal. So I better send the signal to tell the brain, you are actually looking at this particular color. But as it sends the signal, remember the pink cells is in the middle? So what happens is, initially the signal comes and the signal goes over. But when you flood it with one type, right, the pink color cells becomes overloaded. So what it does is, it tries to jam the two signals. But here's how it looks like. So suppose I have a blue and a red. And what you are seeing is that, let's say, right, you are seeing too much of red. But this is linked to the next blue color cell. Okay? So the blue color cell, nothing. So we have red, all right? Red keeps flooding in. You see a lot of red. Now, when you see too much red, it will overload the cells. Remember, the cone cells are activated all the time, correct? Now you turn it off, the bipolar cells will start to signal. But the bipolar cells cannot work forever. If they fire too often, they will die. So one of the functions of that pink color cells you saw just now, the amacrine cells, is that it holds on. So if you keep seeing the same color, what it does is it will try to reduce the firing of that red color cell, the red color bipolar sending it the signal, so that it doesn't overwork and die. But when it presses down, remember, it has also another arm over at this other side, correct? So when you suppress the activity, but this time around it wasn't started, so the signal will be what? It suppresses, and it even suppresses the original, the cone cells down here. All right, you will send, remember you learned before, it's all chemicals when they are trying to transmit the signal across. So the amacrine cells will send chemicals to suppress this part, but you will accidentally suppress this part. But because this was not firing, so you not have too much of inhibition, it will flow in and it will stop the cone cell. So when the cone cell stops firing, what happens? You interpret it as, this guy will interpret it as, hey, why you're not firing? If you're not firing, right, that means there is really a signal. So once you stop the stimulation, so the amacrine then decide to stop, right? It stops inhibiting once you take away that illusion picture. But this side wouldn't know, the bipolar wouldn't know. They are not really brain, they are just signalers. So it starts to fire and you see the opposite color. Okay, let's make it simple now. Now that you have all the things, let's put it into structure for you. Simply put, our cone cells are always arranged in opposite colors. And the regulator cells will have its grip on both sides, but the regulator cells can only turn on or turn off. So in order to protect one side that is overfiring, it turns on and start to suppress the signal. But it will also affect the other side that is originally not firing. But when the regulator over suppress the other side that is not firing, okay, the cone cells of the other side literally stops firing. But this will give a false signal to the bridge, which is the bipolar cells, the originally not firing bipolar cells. Then it realizes, hey, if my signaler is not firing, I should fire. So now this part will send a wrong signal for some time until your brain gets tired and tell it that, hey, wait, enough of blue. Then it will stop. All right, then the amacrine turns on again to stop this. And when it stops this, they will have a chance to reset. So in broader picture, it means that when you were looking at this, you were feeding yourself, for example, right, the green color, you were feeding yourself with too much green. So eventually the amacrine suppresses the green signal, but when it suppresses, it will turn off the red, the opposite part, right? The red color cones. Then the bipolar of the red color one decided, hey, why are you not firing? It fires off. So after you switch to a white screen, you start to see red over here. Got it? So the opposite of black is white. So if this whole thing, and then the opposite of yellow is blue. So eventually you see the red, white, blue of the American flag. Okay? Now, so what we have is that at this point, you find that they can only explain how the perception works. They can't really make this applicable except for fun illusions. All right? But it provides way back then. So all these cone cells, they were first discovered sometime in the middle to late 1700s. So at that time, you find that all these optic things, they took a long time to be discovered. For millennia, all right, actually humans were trying to figure out how we could see things. In fact, the most popular theory was that our eyes shoot out some kind of invisible beam, it touches something, and therefore we know what's happening up there. It wasn't until about 1,000 years ago, all right, in what is known as Iran today. Back then, it was part of the Persia Empire. The so-called scientists back then, right, actually just one scientist. So that genius, all right, did some experiment and discovered that we actually receive some kind of unknown particles from elsewhere, and we are able to see things. So that started the idea of how light propagates. But then people wondered for many years why we could see colors. So in sometime around 1789, two, I think one of them is English, Young and one guy is called Young, the other is called Helmholtz. So they actually put together something independently, and together it showed the cone cells. But they didn't have all the instruments today. What they did was they behaviorally have people look through things and they figure out that there must be only 3 kinds of cone cells. And it stuck until today, where we finally, right, over the past 15 years, we start to realize maybe there's one more signaling, which is yellow. Because all along it was always thought that yellow is simply what? Is simply some proportion of your red and your green combined together. Okay, but now we have some evidence suggesting that it's not a combination. There seems to be an actual unique thing by itself. All right. So you find that all these discoveries actually span out 1,000 years. Because these things are so microscopic, no one can study them. So no one could understand how humans actually perceive things. And they couldn't explain, they had all this back then, but they couldn't explain why people can be so-called short-circuited. Okay? So this laid the foundation for subsequent work. So at this point in time, you find, wow, so theoretical, oh, so dry. Yeah, because we are now revisiting what happened sometime in the past when people laid the foundation for understanding perception and how to twist it. All right. So this is what I mentioned just now. All the amacrine cells, how they block, how cells are usually arranged. And you find that then this connector, right? Notice it's always connected to like the opposite. Then some cells will, if they actually grow, all right. Now this is a simplified diagram. It doesn't show you how the amacrine actually regulates it, but it is simplified to show you that, you know, sometimes signals can increase, sometimes it can be inhibited. All these signal, this add-on or decrease is actually the work of the bipolar and the amacrine cells. I don't need you to memorize how they work exactly. Okay, if you are into a more advanced module, then yes. At foundation, we just need to know there's something there modulating the thing, and that's why we are able to short circuit them. Okay, and the other thing that usually people need to demystify is that it's not because the light energy hits us and then it stimulates. It's actually what the light energy hits us and turn off our cone cells. That's why we see things. All right. Now the last part is this. This one I will need you to imagine a little bit. Okay. Hopefully you have experienced something similar before. Okay. I can't recreate it in here because we need colored lights. Now I'd like you to imagine you're in a concert. In a concert where they have special spotlights, right? So suppose, right, your favorite celebrity is now on stage. Now, there's a bright yellow spotlight on the celebrity. And you can clearly see he's wearing something like a shirt, yellow shirt on top. And then it's a pair of jeans, all right? A pair of jeans that he's wearing, all right? So top part is some kind of shirt that's now yellow in color. Bottom is, you can tell it's jeans. Now, here is the thing. Can you tell me what is the actual color of his shirt? It could be, but why can't it be yellow? If it's a yellow shirt under yellow spotlight, it will appear yellow, correct? If it's a white shirt under yellow spotlight, it's still white color, it's still yellow color, right? So now, can you tell me what's the color of the shirt? Kind of difficult, isn't it? Because you can't say for sure whether it's yellow or it's white. Now, consider the jeans. Jeans are more unique because we not only have colors, but we usually can see the texture. All right? If you are close enough, I mean, if you are standing far back, then that's another story. But if you are like, front row, all right, and you are dancing to the beat, yeah, you usually can tell. Okay, here's the thing. Now, if it's a black pair of jeans, it will still be black under yellow spotlight, correct? So now you see the jeans, to your eyes, it's green in color. What's the color of the jeans? Blue. Now, the thing is, you can tell yourself that you can tell yourself, I'm seeing him wearing green. But what does your mind actually tell you? Is it blue or green? That's what our mind does, right? It usually overrides that sensation. Now, clearly, our eyes will see green because of the mixture of color. But your mind will tell you, I know this is jeans, and it must be blue. You can't, just like when we first started this lecture, you saw the Dalmatian dog. You just cannot ignore the Dalmatian dog, right? So same thing. Now apparently for colors, it's also the same. So what we have is we realize that the brain is not just leaving everything to your cells. What it does is it has a top-down processing, meaning once it has learned something, it will try to feed back to you through your experience. So it will make sure you see what you think is correct. But then that's dangerous. How do you know that what you see now is what you've seen before? Okay? So we cannot trust our eyes fully. We sometimes have to rely on instruments. Okay? So in other words, color perception relies on three mechanisms. One will be the most basic physiological. That's the trichromatic theory, which tells you you have three colored cone cells. Then we have the cells that are arranged, the cone cells, right? They are arranged in opposites and regulated by some intermediary cells. So this can be short-circuited, and this part, right, is called the opponent process theory of vision. Please remember to put in the word vision over here. This is in point format. But if you are talking and you are saying the word for the first time, just say it's opponent process theory of color vision. That's the full term. Because opponent process, this term, right, it appears in a lot of literature. You see it in physics, you see it in other areas of psychology, you see it in what else? I think in other forms of biology also you see it. So it's like a very general technical term. Okay? So over here is the opponent process theory of color vision. And finally, there is the top-down, your brain wins the day, Retinex theory. All right? Now, after they discover all this, right? So this is like, this part was the work to understand trichromatic theory started in sometime in the middle 1700s to late 1700s. Opponent process was newer. I think it's about 80 to 100 years ago. Okay. Then this part is about 40, 50, no, now it should be 50, 60 years ago. Okay. So throughout this 1,000 years, we finally understood how we can actually perceive light and color, and what are some of the mechanisms involved in it. Now, what I need you to remember is that there are three processes. So put a star there. There are three processes. If you read in textbooks, when they tell you there is a bottom-up process, it usually refers to this trichromatic theory, where bottom-up meaning how you perceive, it depends on what is at the lowest level of the arrangement. In this case, the cone cells, because they are the ones that receive the light signals first. The top-down processing is usually this Retinex theory, which tells you that your brain has overriding control of your perception. So now this answers a question. Whenever people ask you, so you think we are able to interact with others and the world, right? Is it because of the input from them, or is it because of our previously learned behavior to interact with others? This applies not only to color vision, but to all our behaviors. In fact, they are both working at the same time. We are able to respond, all right, hopefully in appropriate ways, because of information that we process now and then past information. I'd like to bring your attention to the first part of the statement, information that you are exposed to right now. If this information is new and you have no other thing to rely on as experience because it's a novel situation, so that means you have to be creative, correct? That means, and this is the true nature of humans, our sensation and perception is not always about repeated stimulation. There is always a need to also figure out new information and take steps to generate solutions if this new information actually poses a problem. Okay? Keep that in mind. This thing will surface again at the end of today's lesson, or at least the first half of today's lesson. So the rest are not so important. Then there's this thing called color blindness. I think somebody asked me before. I mentioned that there are different types of color blindness. Less than about only 5 to 7% are really totally colorblind. Okay, so we always know that it's a figure less than 10%. Out of 10 people, only 9 people will certainly see a bit of color, even if they are not complete color. Okay, and this is important. The ability to see color. One of the other thing is highlighted in evolutionary psychology. You see, humans are actually very weak creatures. We are fragile. We don't run fast enough compared to other animals. We are also not as aggressive as a lot of other animals. And even if we try to be angry with other animals, you find that they one swipe from them and we're dead. So how did we actually become, all right, one of the top predators of this world? But before your intelligence, you got to survive, you know. And the primitive humans don't have as much intelligence as we have today in terms of tool manipulation. The answer actually lies in color perception. It's been found that actually a lot of animals in the animal kingdom, they are not able to perceive colors. Some animals are able to perceive colors, but they have limited range. They have maybe, say, 2 cone cells. That's what I meant by limited range. Humans have 3 cone cells. So that allows us to have very high resolution images of the world. Any little bit of movement in the distance, we are able to contrast it properly and we run. So animals might have evolved camouflage patterns, but against another, let's say humans versus antelope, the antelope may be able to run very fast, but the antelope may not be able to detect the danger early enough. Humans actually have a higher chance of detecting it. So you see, this is how color perception has already altered our behavior. We may not have the ability to run faster, but we have the ability to react much earlier. Okay? So people who are colorblind, of course, they will have a serious disadvantage compared to people who have full color vision. All right? Why? The answer lies in the resolution of the environment. How clear, how sharp, it depends on their ability to see colors. Okay? Not simply the one-to-one connection between the cone cells and the ganglion cells. All right? Now, oops, I shouldn't have pressed this. I hope I didn't mess up anything.
Is it still showing this? Is it supposed to show this?
Yeah, okay. I can move. Now, the other thing that, that we have about how vision can be, so after they have discovered the full thing about opponent process, right? That means they finally explained it properly. Now they can start to look at the various ways that human vision can be short-circuited. And remember, we talked about the history that Gestaltists came into play. So the Gestaltists started this, but they didn't finish because they lacked the instruments to scan the brain, the eye, and so on and so forth. Plus, they got whacked very severely by the who? Can you still remember? The behaviorists, yes. So we look at some of their discoveries before they got pushed aside for about easily 30 to 40 years. Now, what they discovered were certain rules that can quickly tell us how we are able to see certain things and also how we got short-circuited. So we are always able to see things because our brain switches very quickly, our mind switches very quickly between interpreting a color as either background or foreground. So if you look at this, right, this is the typical vase illusion. Now, do you see 2 faces or do you see a vase? Maybe you see both, but I think you cannot see both at the same time. It's just flipping very quickly, right? Because your mind will either see the green color part as the bluish green part as the foreground. If it sees as a foreground, then you will see the vase. If it sees this as the background, so now it becomes the backdrop, right? You will see 2 faces. But you cannot see both at the same time because one must be the fore and the other must be the background. Okay? So here we understand something about vision. Despite the fact that we have very high resolution pictures, we still cannot run away from contrasting effects. You got to, the mind must quickly think, is this the fore or the background? And this operates at your unconscious level. So whenever you're exposed to something, within about 0.1 to 0.2 seconds, your mind has decided whether to treat it as fore or background. Okay? So this operates at the level of your, way faster than your conscious mind. Your conscious mind will probably kick in somewhere around 0.3, 0.4 seconds, and that's only the pre-conscious part. Okay? So to actually understand things, we already have a quick foundation. Foreground, background, right? Now here is a list. I'd like you to put a star here. For this figure, ground, perception, and this, please read. These are the principles discovered by the Gestaltists. They fall short of explaining which part of the occipital lobe deals with some of these things. But later on, we discover it is not the occipital lobe alone. Your prefrontal cortex will, and your temporal lobe has to also become involved in activating some of the rules. But the rules were first, that means the pattern of behaviorally knowing what we are seeing, that was offered by the Gestaltists before they got killed off by the behaviorists. So put a star there and quickly read through the principles and see if you fail to understand any of it. If not, then I will, that means if you are okay with it, I will continue the lecture. Done? Any question? The words are in simple English. I don't expect any problems, but just in case, going once, going twice, okay. Now, of course, these are only the basics. What actually drove the Gestaltists to try to discover components? You notice these are, you see, if I show you the next slide, this is what inspired the Gestaltists. You've seen this before, all right, the Dalmatian dog. But what they were trying to do was they were trying to uphold a particular school of psychological thought and this school said that we should do experiments to find out the basic building blocks of our behavior. What school is that? Can you still remember? Oh. The structuralists, yes. So structuralism talks about what is the building block of our perception in this case. So when this inspired the Gestaltists, they tested and tested. Eventually, they came up with, they realized that we are operating according to these principles. But before they can look at which parts of the brain deals with this principle, they got killed off. Got it? So that's how it goes. So please put a star here because this tells you the basic stuff. And of course, you might just see it again, right? And of course, it's not just that. Later on, they found that it's not always as in still pictures. All these principles can also be in moving format. So you look at this. It seems like there are several rings turning in different directions, right? But actually, they are not. Look at this. Can you see the starting picture? Yeah. So it's just that the contrasting color actually short-circuited your system. So now your brain doesn't know what to do. It just then interprets this. And it doesn't mean that, for example, I might see this as going, this third ring going anti-clockwise. But in your point of view, you could be seeing it as clockwise. It all depends on how your brain interprets it in the first place. So this is random. We don't know how your brain will interpret, but we know it will be short-circuited. So once this has worked out, it has given the entertainment industry lots and lots of tools to create make-believe worlds. So of course, before the start of digital technology, they used a lot of all these kind of things to create visual effects. So before TV was invented, there was circuses, correct? So circuses not only have animal acts, acrobatics, they also have all this illusion, fun illusion. Then TV came about and they extended all this into what? creating models, but filming it closely, so you see there's a big, big thing. All right, just go Google Lord of the Rings movie, behind the scenes, and you see that happening, okay? Now, all these things, the movement part cannot be explained unless we can also explain how we humans are able to perceive distance. So first off, right, color allows us to survive because of the high resolution. We are able to escape before danger even arrives. The next thing is, so what if you have a clear picture? You got to know how far to run, correct? So this will now, with this, right, it will now lay the foundation of how we behave in three-dimensional space. To be able to see three-dimensional space according to the colors and giving us very clear, resolute picture, and to be able to navigate in three-dimensional space, because we can now navigate through distance. We know distance and we can navigate through space. Now we will really be able to survive plus manipulate tools. Now, how do we see perception? How do we perceive distance? Technically, the term is called depth perception. And there are two mechanisms. They are called monocular and binocular cues of vision. Now let's break it down. Let's look at monocular cues first. Monocular cues are general mechanism which animal kingdoms, a lot of animals will have too, especially animals with a long snout. Dogs, foxes, wolves, right? Cats are the exception. They have evolved to be without a snout. All right? And if you think about it, horses, sheep, so a lot of animals with a snout, they also have monocular cues. This is a weak form of telling depth. What do I mean? Now, there are certain things that were discovered by the later, some of the minority Gestaltists, and later on, right, when they were pushed down, some people were still working on it. First off, how do we know whether something is distant? Oh, yeah. Now, here's where I'm going to ask you the question. Look at this picture. Now, I'd like you to tell me what is the distance from this spot, right? So suppose, imagine someone is standing on this black silhouette spot and someone at this far away mountaintop. Can you tell me what's the distance between these two spots? Mr. Lam, you're crazy. Actually, the distance between these two spots, let's go all the way to Edwin, right? Okay, so actually there is a way to tell the distance. The distance from this spot to Edwin is probably around somewhere between 4 to 5 meters. Huh? What? Yeah, because it's really the distance from the TV to him, right? But how come you see this spot, this black color spot, as what? Maybe several hundred meters, like this is say. But this mountaintop will probably be a few kilometers away, correct? What is happening is that there are certain illusions. Monocular cues work on what? Some sort of illusion. So whilst the illusions occur, earlier on you learned that illusions occur because of short-circuiting the system, but there is a need for them to function, actually. So, first off, if we paint a picture where some parts of the picture are clear, some parts of the picture are like blurred out, like this. Notice the back part is actually blurred out a little bit. And you think that it's actually cloud or fog there, but maybe the artist simply wanted to put it there. But whenever we have something that looks clear, this is maybe a silhouette, but the black color is very clear. It's nothing just black there. So it already gives us the illusion that the mountaintop is actually further away from the side of maybe this cliff. Then, if things are positioned higher in the two-dimensional plane, like for example, if you look at this spot, the cloud here, versus a spot over at maybe the mountain here, then versus a spot that's a dent here, we can clearly tell this is nearer to us, right? The part I'm circling. And then here is debatable, but most people a lot of people will actually answer, oh, the sky probably further away, because it's higher up. So when you are given all the things that are seen from the real life is projected onto your eye, it becomes a two-dimensional picture. But your mind has learned over the years, evolved certain rules. One of the rules is, if it's higher up on the two-dimensional plane, it's probably further away. Okay, just can't tell the exact distance, but it's probably further away. Now the rest, I use this picture to show you. If there are some kind of cues in the environment that has two lines, all right, meeting at a spot, then the spot is actually further away. All right, if there is overlapping, the covered picture is usually the further away object, and so on and so forth. So this one you can read about it. I think I will just focus on one more, texture gradient, because it's not immediately clear. Texture gradient refers to the whether the objects, right, have high or low resolution. Now, from this simplified picture, you actually see that there is more. You notice the artist actually added more strokes to the bottom, but lesser strokes on top. It already gives you the illusion that you are looking at a field, all right, but this part of the crops are closer, but this part of the crops are further, right? So texture gradient really tells you the density, the amount of detail packed into the picture. If there's a lot of clear details in the picture versus lesser, like clustered detail, the clustered detail is usually deemed as further away object. Now, these are all broken down components to show you clearly. In real life, this is how it looks like. Notice you have linear gradient, tip of tongue, let's go back. Linear perspective, yes. You have linear perspective here, railway track. And it's not all. The linear perspective also comes from the cloud, right? And furthermore, the darker spots are usually further away. So you notice the darker spot actually matches with the converging point of the lines. Where this part of the cloud, and some people might see this one, although this is higher, but they may see, oh, this is like nearer to us and this is further away into the distance, right? So texture gradient, look at the tracks. The gravel that is paved onto the track, notice there's clearer details here, right? But the details are no longer as much. It's like all mashed up stones already, tiny dots only. So it gives us the illusion of whether a spot on the picture is nearer to you or further away from you, when they are all just about 4 to 5 meters from Edwin, right? And this has given artists a lot of room for creativity. You notice that artwork has gone through a lot of changes. Like they have started with what? Maybe they have very abstract art, still life. Eventually, when it comes to what? Realistic art. So they literally draw with all this. And of course, then there's the Renaissance period, and a lot of things change too. So basically today, all these things, they when whatever feelings or whatever texture the artist wants to show you, they will fall back on, okay, what do I need? And then they will figure out not only the color, of course they still have to add on their kind of work, like the color, the shading, the thickness of the paint, okay? But very quickly, they would have processed all this and know what they want to draw, all right? This last part, motion parallax, refers to what? Whether a further away object usually looks what? Look less blur because it's not moving, right? Just go take an MRT train. If you are a driver, if you drive a car, never mind, just park your car somewhere, go take the train for one station, then stand at the window and you look outside, you find that things further away, all right, it doesn't really move much. But if you stare at the track, well, it goes blurry, because that kind of thing, when things are moving, this is relative speed. In physics, it's relative. To your mind, it means that I don't have enough time to capture the image. Because it's closer to you, the relative speed is faster, and so it appears blurry. So over the years, when the mind realizes things I cannot capture fast enough, it must be closer to me. Got it? Okay. Now, all these cues, put a star there. The explanations are in this is the example, the explanation is here. Okay, so this one you should know at least some of them. Maybe you can't remember all of them, but at least know some of them. Some meaning maybe 3/4 of these. Okay, Okay, I'll come to that later. Let him finish taking picture first. Okay, now I will answer Stephanie's question about motion sickness shortly. Let me finish up with depth of perception first. All right. So the other mechanism is called binocular cues. Here you don't have so many features, but the real thing behind how humans can manipulate tools very finely, like if you want to push a thread through the eye in the needle, you need binocular cues. So animals, even if they evolve hands, they will never be able to do this without binocular vision. All right. So that's also one reason why there is no need for certain animals to evolve hands, because they are not able to process information the way humans do. So instead, they need to run fast away. They evolve maybe say hooves, all right, to be able to stamp the ground, all right, without feeling much pain. And therefore, they run at what, 40, 50 kilometers per hour with 400 kilograms of weight, all right, pounding the ground, but not feeling any pain from the hooves. But this binocular cues, the technical term is called stereoscopic vision. This is the true ability to see three-dimensional space. How? So don't lose any one of your eye. I mean, if you lose both eyes, you're blind. Okay? If you lose one eye, you have to fall back on monocular vision. So don't believe too much about Pirates of the Caribbean movies. Pirates don't just put on one eye patch and show off and then swing right from board to board when they want to board another ship. If they try to do that, they will end up like the blind Tarzan, smack into a plank and then fall dead. You need stereoscopic, so it's not true that pirates always wear a patch. Why? You need two eyes to do this. First is the idea of convergence. Meaning what? Now, this part I'm sure all of you know, and you can even feel it. What you need to do to feel it is you put your finger out, focus on this thing, and move as close to your eye as possible. You probably will feel a strain on your eye. Why? Your eyeball is closing out, right? Actually, every time your eyeball moves, so if I blow it up, let's say I'm looking up, okay? So my hand represents the eyeball. So the eyeball rotates to get a focus. The more it rotates, the closer the object to you. And over the last few million years, the eyeball and the brain has learned that how much convergence equals a very specific distance. So if I look at the camera now online people, you probably can't see you because you can't see the camera, okay? But I can easily tell that this is about 1.47 meters. I'm kidding you. No, I can't see the exact cm, but I can definitely tell maybe round off to 10 cm for close distance. In fact, this thing, if you go further, let's say you go up to 50 meters or 100 meters, you probably cannot go by centimeters, but you can go by a few meters. This vision is good up to about 200 to 300 meters, depending on whether there's training for the person and whether the person has aged and experience. So that's why, right, the army, when they train people to shoot, the range is it ranges all the way to 300 meters. But nowadays, I heard the basic military training, they dropped the 300 meters. So I don't know whether they still get trained to shoot that far, okay, but they are shooting at 100 meters, okay? But in the past, we got trained to shoot up to 300 because that is how far this mechanism can be good at, okay? Then the next thing is, that's different. That's why with training, you can push this. So there are certain African tribes, they have shown that some of these natives, right, they are actually able to see a coin at 500 meters away. And they can tell you the coin, how much is it? Not many of them do that kind of training, but they have. And it's an ancient art form that is passed on. And some of if you read up anthropology, you find that they actually introduce you to this kind of things. Okay, so some of these people, they still maintain this, they learn it from their parents or what, so they keep that art form. It's of course useful for them to hunt in the past. They're probably not going to throw a spear 500 meters away, but they want to be able to see what animal there is. Okay? Of course, they overtrain. It's the same as Shaolin monk. When you overtrain yourself, you really can fight for long periods of time. And the people in the mixed martial arts arena, they adopted this practice, right? They overtrain themselves. Overlearning, we will learn this next week. You find that it's a very useful thing, okay? But it's very time consuming to reach that stage. So you ask about snipers, they actually have to overtrain in two things. One, learning how to make use of things to camouflage themselves. Actually, three things. Camouflage themselves, learning to control their breath so that they can, and vision to shoot at far away distances and shoot stably. The last is actually patience. Yeah, one of the most astounding snipers in the world happened, I think, in Vietnam War. So this guy was like crawling at the speed of about 30 cm a day. That slow. So it took him, and he didn't dare to eat or whatever, but he crawled after about 4 days. He would drink water from the dews and all this. About 4 days, he managed to crawl, so without being detected. I can't remember his name, and he wasn't an American. The Americans actually made use of, I think he's a Filipino. So he was enrolled in the US service. And then eventually he was so near to the target that the American wanted X, and he managed to shoot that guy. Okay, so he became a very feared sniper. So they have to overtrain in a few things to make things work. All right, so that's about overlearning. But let's come back to here. Retinal disparity, you can also experience this for yourself. All right, put out your maybe your hand. You don't have to put it all the way out. Just, you don't have to fully outstretch your hand, just a bit bent. Now, if you close one eye and close the other eye, you'll see different images, right? Just put your hand in the middle, close one eye, close the other eye. Now, but you take it away, you either see two images, correct? Now, if you force your eye to converge, you should see your hand now. But the thing is, actually, the two images are different. Because one eye shows you the back, the other eye shows you the front of the palm or the hand. Now, how come the picture is like one smooth hand? All right? Because the most powerful and earliest Photoshop tool is actually your brain. It's not Adobe. Okay? When your brain sees two different images, it will start to Photoshop and try to piece it together. Of course, remember I mentioned before, your eye darts like every 0.3 seconds. Now that will help. It will help with the Photoshop. But so instead of giving you strange pictures where it's just smack superimposed, it tries to smoothen out and you see an object. So you are able to see three-dimensionally the object, and you're also able to tell the distance depending on how much the brain is actively doing Photoshopping. But the brain won't tell you. The brain will just swiftly Photoshop, and in a split second tells you how far that thing is. So you can reach out for your glass of water. You can when people throw a marker at you, you can catch it in midair, provided you are a bit trained. And of course, depending on how fast it's flying, right? So all these are actually retinal disparity. The greater the disparity, meaning the greater the discrepancy in the images, the more the superimposition, the more the Photoshopping, the closer it is to you. And the brain over the last few million years has worked out how much Photoshopping equals roughly how much distance. Up to, when it's close enough, centimeters. If not, it will estimate by the meter. Okay? So you can react. And how does this? Now, you may not have paid any attention to this. So suppose, borrow your cup, Ken. Does it have water?
Yes.
Oh, okay, I'll be careful. How do we reach for, let me stand back so that the online people can see. Yeah. How do we reach for the cup? Most people just say, it's simple, I just stretch out your hand. Did you actually know that your hand, when you move out, it's accelerate, in the initial moment it accelerates, constant speed, and decelerates. Furthermore, next time I think it's very difficult for you to try and feel it, because when you feel it, you might override it. But if you can somehow capture a picture of someone doing it, right, you'll probably be able to analyze this. Now, if I were to, I can't use this because there's water. Maybe everything. Let's use this. So I can tilt it, and then you can see clearly. Moreover, your hand is what? Even before you start to reach out, right? So I'm going to reach out. I already have estimated, because of binocular cues, the size of this. But I'm not going to adjust my hand to fit this size. Instead, right, there is still a lot of room for preparation. So you notice every time we go out, right, we start to what? We may pull back a little bit, but we will extend wider. That's the early phase. So acceleration time, you will extend wider to accommodate, to adjust. So your hand-eye coordination, everything is calculated. Your mind also knows whether you will reach it on time. It's all about 3D manipulation. But when you are about there, you are already closing. So it's like this. You don't. That's robot. Or primitive robots. Nowadays, robots also don't do this. All right? So this is one more cue. When you are doing this, actually, your mind is getting what? Feedback. So initially, it's using all this binocular vision to calculate, to estimate. As it goes out, it's this extension, all this, later you'll learn proprioception. It gives the feedback, and it's the confirmatory signal of whether the binocular vision is accurate. So you can then manipulate very fine tools. For primitive days, the fine tools will be just what? If they can even use a rock and smack another rock, it's already very fine. Of course, today we talk about fine tools as what? Maybe using mouse, right? So these things are all part and parcel of how you behave. And these are all the nitty-gritty details of your sensation and perception. Yes, I know it's heavy, but I thought we have overshoot the time. Okay, let's take stock first, so that you can be clearer before we move on to the next topic. I think one or two more topics we go for break. First off, let's look at how we perceive things. Why do we even want to know how we perceive things? Because it's the root, the foundation of our behavior. You can have all your neurons. No, don't look at the board. I'm just recapping what we have covered. All right, so pay attention. The way we behave is not just simply coming from our neurons as you have learned it before. The neurons cannot work unless it has a way to interact with the environment. This is first achieved through sensation and perception, which you learned it last week. The definition: sensation is the energy from the environment or from another person, maybe from your internal environment. All right, it converts to some energy that you can register. Then the way you organize these kind of energies, these signals, that's perception, right? But we learned that the most important tool for us to interact is actually our vision. For humans, okay. For animals, maybe sense of smell, right? So for us, it's vision. Then you learn the first component of vision, which is what? Color perception. Most people think that color, we just take it for granted. But now you realize that with color comes resolution, sharpness. That's how, and an ancient application of this was how we survive against animals. We can't run fast enough. We escape first, right? And then you realize that the mechanism behind color vision has 3 types. We make use of 3 mechanisms in order to sharpen this system. What are they? First is trichromatic mechanism, right? Or trichromatic theory of color vision. Next one, opponent process. Although this is easily short-circuited. The third one fully relies on your brain's learning capacity. Bratignac's theory, right? Great. So we have 3 mechanisms we use to tell color. And from there, we move on to looking at the other important component. There are 3 important components that allow us to fully utilize our vision. So the second one is the ability to tell distance. With that, we can now maneuver ourselves in space. And there are 2 key mechanisms there. One is monocular vision. The other is binocular vision, correct? Okay, so that is the thing that helps humans the most. And only a few species of animals have that. So cats, some types of birds, humans, and dolphins. All right, but then the underwater creatures, they don't really use that much. They usually evolve some other more important tools too, like sonar navigation. All right, so they actually send out radar signals underwater and then listening to the echo. Okay, or they rely on some other things, maybe electricity. Yes, in underwater current, there's a lot of salt, right? So salt solution is a good conductor of electricity. So all these sea animals, they actually rely heavily on electrical signals in the water, electric current, for their sensation and perception. Okay. Now, so for humans, we look at vision. We look at two important things: color and depth perception. All right. Now, the last part we are doing is how our mind actually interprets all this information in a stable, can be clearly understood form. And this is called visual perceptual constancies. Like, how come you are able to see brightness and light or lightness in a very consistent way? What do I mean? Now consider this. I'd like you to imagine this. You are walking under the sun, so you should appear very bright, right? Then you walk underneath a bridge, so you will have a shadow cast over you. Will you be still as bright looking as you are? No, so you actually have a tinge of gray. Then you move on to you move out of the shadow, you become bright again, correct? But another person looking at you will interpret you brightly, still you, but darker, and you again, but now brighter, correct? Now, how is it that your mind doesn't tell you a difference between the bright and the dark thing? Because they are actually two different kinds of sensation. One has more light bouncing off you, so it's bright. Now, to you, you find that, what is this? I really can't understand what you're talking about, Mr. Lam. Because it's so instinctive in us. When we imagine the scene, we imagine, yeah, it's just a person going through. Because you are already applying all these mechanisms. To, let's say, an alien that has come and has never been able to see the way we see things. So first time they have vision, they are going to find it very weird. Why is it that this thing is bright and then suddenly it's dark? Are there two objects? The color itself is supposed to tell you that it should be another object, but we don't. We simply look at it tracking. I'll give you one example to help you clarify. You take a lot of things for granted. I have a patient, she cannot cross the road like that. Why can't she cross the road? She can walk, she can see things, so she will walk slowly. But now let me go back to that road. When you are supposed to cross the road, what are you trying to avoid? Cars. Cars don't move as slowly as humans, right? Most of the time. So when they are moving very fast, her brain, right, because of a stroke, she could no longer interpret things as the way we interpret. So a car in the distance would appear smaller, correct? A car nearer to you would be bigger. But these are two different sizes. So to her mind, it's two different objects. So now the mind makes her see things like this. It's going to be, this is as best as I can describe. It's probably not even close. So what she sees is actually there are a lot of cars flashing. Same car, even if it's one car, right, it's flashing. So it's like there's a car, and suddenly it disappeared. Hey, another car here, it disappeared. Now, if you are trying to cross a road where the cars are like teleporting themselves, how are you going to cross? You can't cross. You don't know when the car will just teleport right in front of you and run you down, right? But that's what she's seeing. Because her mind refuses to think of sizes as the same object. If there are two different sizes, because it's just one in the distance and then later on it moves closer. The mind thinks that it's two things, so it will block out the middle information. So the car like appear when the mind happily randomly decides, that is a small object. Okay, never mind. Oh, that's another big object. So it flashes. She cannot cross the road without assistance. Okay? So brightness, same thing. If another part of her brain was damaged, she might see you as, oh, this is you under the in the sun. I think that one must be your twin brother. It looks darker. Okay. So we are able to Photoshop one last thing. All the images are put together, every little bit of detail calculated, so that you interpret them, the brightness, the changing brightness, the changing color. I will come to this shortly. And the changing shape and sizes, they are, why changing shape? Like this. This is what kind of shape? Something like, let's make it simple, rectangle, correct? But now, what is the shape? But you know it is still the same bag, right? So, oops, oh yeah, I think they can see. So the point is, all these things are seen as one object because your mind pieced everything together and Photoshop them into a continuous picture for you. And we thought this is like, we take all this for granted. So you better touch wood that we never ever go down with stroke. Otherwise your world will change. Not only half side cannot move, even if you recover, you might not recover fully, your entire world will change. All right? I have a patient, you give him a bowl of rice because he has hemi neglect. So what happens is he will eat, then he said, I finished eating already. At least he signaled. But you look at the bowl, right? You find that if this is the bowl of rice, okay, he will eat about half. Then you just rotate the bowl 180 degrees. Say, oh, I haven't finished. Then he will eat again. Okay? So a lot of things will change. You will not be what you are anymore. Now, here is a video for you. I got to pull back.
Your video that went through, right?
No, not yet. This appears very different. Oh, yeah. Okay, let's take a look at this.
The checkerboard illusion. You might have seen this one before. There's a similar one in your book.
Do I just share screen this thing or what?
Or
I push it to the other
I
side?
think you push it to here. Would it be easier?
I don't know. Okay, let's try.
Yeah, maybe you push it to here.
Push some more. Okay. Yes.
Let me see.
Wait, I just need to blow it up.
Yeah.
Okay.
That's perfect.
Okay, here we go.
The checkerboard illusion.
Look at the way your mind actually helps you understand the world, but it's actually giving you false information. It comes from here.
You might have seen this one before. There's a similar one in your book. And when you look at this illusion, it looks like square A and square B are dramatically different colors.
Correct?
However, they're
A and B, are they the same color or are they different color? What do you think? Different color? Okay, now let's continue.
exactly the same. And because I know you will not believe me, we're going to go and we're going to open up Microsoft Paint and we're going to demonstrate that A and B are exactly the same. So I'm going to just take a little piece of square A and I'm going to start dragging it towards square B. And as I drag it, it really appears to be getting lighter. That's because our brain is applying different contexts to our interpretation of that color. When square A is all the way out here at
Anyone
the edge
expected
of
the color to change? That it's actually, this looks darker, right? It's supposed to mimic the black color on checkered boards. And this is supposed to mimic the white color, but they are actually the same. What happened is Retinex theory is partly at play here. your mind has learned that if there is some tall object blocking off the so-called light, because this gives the illusion of light source on this side, so there must be a shadow. So it's now adjusting all the color until you see it nicely, like how it's supposed to be. But in actual fact, the colors are the same. Okay? So you see how nicely your mind treats you? In order that even on a fake picture, that you can still work on it, it gives you the illusion so that you can function. All right? So now, do you still believe what you actually see? I think I have uploaded this. You can go and see. I don't know what else she has to say, but you can go and watch this. Let's go back to Oh, I need to wait for this to come down, right? And then I go back to the slide.
Yes.
No, the sound thing will come later in the class activity. Oh, yep. So you see, your mind constantly plays tricks on you so that you can navigate around the world. So this debunks the myth that, well, once we are able to see things clearly in what they are, we will then be able to function. If you see things clearly as what they are, you wouldn't be able to function. All right? So when does it switch into trickery mode? When does it not? That depends. And you notice you have actually no awareness of this. And it occurs at a split second and you're able to react. So that's how far we have come over the last 1.5 million years. All right, when in the beginning, we probably can't do this. Detecting light is just like an earthworm. You shine a bit, then the earthworm just shun the light. Okay? Now, last bit on messing up your mind. So there are ways where people found that if we put all those linear perspective across, something like that, we will be able to short circuit the mind, and it's true. So these are two very common illusions. In fact, most people are used to the Mueller-Lyer illusion. You look at these two lines. Now, by now, most people will know that the vertical lines, they are the same length. But if you look at it, right, do you actually see the left one longer or shorter? Yeah, longer. Huh? So it's like, can you check for me one thing? If I stand here, are they still able to see? Can we check? I have to switch. Never mind. Then I will just constantly adjust this just in case. Okay, now.
Yes, you can see it.
Now I have already turned the camera. Anyway, doesn't matter. We can't force ourselves to see this as the same length. Now, the first reason is simple. What happened is, when your eye jumps across, remember your eye doesn't focus on one spot for too long, so it jumps. Now what happens is it will jump also to see this point here, then you will jump back. But remember, this part, it jumps, let's consider this point and this point to be level. Now your eyeball will actually jump a bit further, then come back. But over here, your eyeball will jump closer because it will then level with this spot and then jump back. So this gives it the first incorrect information. But of course, it will not just interpret based on this, it will see as the whole thing. So it will still feel that maybe it's the same length. But there's more than one problem here. Next one is the way we understand three-dimensional world. You look at a three-dimensional, this is a three-dimensional drawing. If you want to, you can of course consider the corner there, all right? And a corner that is like here, closer to you. I don't think I can go close enough to point. So let's just use this picture. Now, if you are standing at a spot, let's say not like this person is just put here to show you that this is a wall. But let's say you are standing here. Now, this is a wall that is closer to, so look, the spot is right here, okay? Now, because this corner is protruding towards you, it's probably nearer to you, right? And this is further away from you. Now, but if we all know that if something is further away from us, it should be smaller. Yet, this is drawn the same length as here. So you look at this spot, to this spot and compare it from this spot to this spot, they are the same length. Now, our minds cannot understand this. Our minds know that from monocular vision, if the thing is further away, it should appear smaller. But look at these two, then it says to you, but look at these two things. They are the same length. So obviously, they cannot be really of the same length. Because by right, the further object should be smaller, but now since the further object is the same length as this nearer object, then originally the line on the left should be longer. So it keeps telling you longer. No, the left side is longer. So you tend to get that illusion. No matter how you force yourself, you can't override the Retinex theory, the top-down processing part of your brain. You are just not top enough. The boss is really your brain. Okay? It's only giving an illusion that you are the boss. Okay? So sometimes people tell you, do you really want to be a slave to yourself, your this, your that? You are already a slave. Hello? Okay? So that's how the illusions are like. All right, let's finish up. In a nutshell, what we have learned in the beginning is how you are able to navigate around the world, how we are able to survive by relying on our most powerful organ for sensation and perception. We don't only have one organ, right? We have talked about now, luckily you've just covered the bulk of it. So this is like, the heaviest is like a lot of details, showing you how the basis of our behavior is really because we have a lot of sub-tools to carry out the work of that one, the function of that one organ, vision. Okay? Now we go for a break. 20 minutes later, we will look at, now I will start off with a class activity first. Then I will talk quickly about the remaining sensors won't be so heavy. And then we will end off again with a class activity. All right? I'll see you at 8:50.
Mr. Lam, no sound.
Okay. Now I have sound? Yeah, that's okay. I think have. Okay, basically what's going to happen is we are going to do an exercise and you're going to watch a video. So this video is not educational video, it's just something like a movie clip, some kind of clip. Now, okay, I won't tell you what it is yet. You watch, then I like you to, after that, right? So we watch for maybe say 4 or 5 minutes. Then I like you to quickly take 2 minutes and pen down what you feel about watching that video. So what you feel, right, should not be simply, for example, if you watch a scene with a bird flying past, you shouldn't be summarizing it is a show about a bird flying. Okay? Because remember, I asked for your insights or your feelings in addition to the scenes that you are going to watch. Okay? All right. So let's try this first. Then later on, right, at the end, we will watch the same clip again. Oh, it's on already. Okay, it has no sound. So just watch because it's a video. Maybe I start it again, huh? Ready? Online people, ready? Okay, here we go. I cannot. I started it. Yeah, so he moves off. Let's stop it here. This is a good segment to stop. All right, now pen down some of, this is a free flow writing thing. So you can pen down your insight, your feelings, or maybe some, unless you've watched this before. After all, this is taken from a Blizzard game, right? But anyway, that would have a different sound effect. So anyway, pen down your thoughts, your feelings, or your insights. Try not to write like a 500-word essay, because we don't have time for that. So keep it short. After you watch it, what's your thought about it? Time's up. Now, maybe you haven't finished writing, it's okay. Just hang on to whatever you've written. Okay, we will resume this. So this is part 1. Later we will look at part 2. All right? And then I have something to share. But let's move on first to sound. Okay? Yeah, I turned it on already. Okay, so the physics about sound, this is just for recap. In primary school, secondary school, we learned that sound, or let me put it this way. There's a question usually on the internet. If a tree falls in the forest, but there's no, let's not consider animals and insects, okay? But there's no human around around that falling tree. So is there a sound produced? Yes, no? Now let's put it to a vote then. Online people, I think you can click on the voting button, right? There's a hands up thing. So I repeat the question. If a tree falls in the forest, but there was no one anywhere near it, Is there a sound produced? If there is a sound, but we just don't hear it, so is that a sound or no sound? Is there a sound? Okay, let us say our vote, right? So, okay, yes, raise your hand. Later we'll see how many no's. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, no? All right. Then this is the time when the wait, look at the online people. Did they click?
Yes, kind of long. One, two,
All the ones for the yes, because just now I asked the question, right?
8.
There should be a number at the side.
It's like that.
Don't know. I don't know. I saw Liz did it.
9.
Okay. So we have people with hands. I think you are talking about the yes, right?
Yeah.
So there are about 10 to 1. So not bad. One from online and one from the class. Y'all can. Too bad y'all didn't start the bet first. Otherwise y'all have one big time. No, there is no sound. How can it be, right? Well, sound is a perception. If no one is around to interpret that sensation, it did not exist. But when the tree fell, of course, there are changes in energy. Of course, there are changes in compression of air layers. But you're talking about the word sound, right? Ah, damn. You tricked us again, Mr. Lam. Yeah, I know. So sounds is very limited to talking about a certain human experience. It's the experience of you detecting pressure, changing pressure in columns of air. And we have a certain limit to this detection. So up to now, it's just a recap. The limit is if the compression and expansion of air occurs at somewhere between 20 times per second. So it's like if this one requires a bit of imagination because all of us know that air has no form, right? But abstractly, you can think of air as what? Layers and layers of super, super thin air, all right, pieced together, layered by layered, laid side by side. And when you disturb it, it's like the ripple on the surface of water. So it will go like this. And then of course, the other layers, right, they will all go like that. And this is the thing, we are trying to detect this. If they go wide, smash together, then go back to their original distance apart, that is one cycle. We can detect somewhere between 20 cycles per second to 20,000 cycles per second. Do you agree with that? We have done all the recap from secondary school. Do you agree? 20 hertz to 20,000 hertz. This is an omen. Do you believe? Yeah, it depends on age. Most people should not believe that it's 20,000 hertz. In fact, somewhere around middle 20s to about 30 years old, you probably already lose 1 to 2,000 hertz minimum. So by the time you are 30 to 40 years old, you probably can only hear about 15,000 hertz. So the lower part also is very difficult, somewhere around 30 to 15,000 maybe. That's why at one time, I think a few years back, there was a very famous ringtone. Usually all the teenage kids will go for it. It's the secret ringtone. But it's actually a very high-pitched tone, about 17,000 hertz. But most parents by then cannot hear it. So all the children will get here, and then their boyfriend's girlfriend call that ringtone. So they know, but the parents will not know. So that's the idea, okay? See? So once you know something, you can start to sell it. Okay, but I come back from selling, right? Now I share, I don't sell. Let's finish up with the recap. You also learned that sound waves, there are only two qualities to it. One, it's pitch, the other is loudness. All right, technically converted, it's frequency versus amplitude of the vibration. Now, what does that mean? So in terms of experience, pitch would be what? No, I'm talking in a very high pitch and a very low pitch, right? But you notice the volume is about the same. But if I speak very softly versus very loudly, the pitch didn't really change, but the volume changed. So that's the idea. Pitch, frequency is how sharp the sound seems to be for us. Volume is how much impact you will feel. All right? Of course, if you convert it to waves, you see this. Right? Okay. I think we're done with all the secondary school recap. Now, this is not something we can perceive all the time. In terms of loudness, there are certain scientific units for it. If you measure in terms of decibels, how loud the sound can be, then it follows this particular range. I don't need you to memorize this, okay? So you just need to remember that we are listening to pitch and loudness, all right? And somewhere around 120 decibels, which is very loud. If you want to experience this, you just go to sneak into the airport, the runway, and try to go very near to the runway, but don't be in the middle, otherwise you will never get to hear it again. Okay? Then when the plane is about to take off, you should be able to hear what this means just once in your lifetime. After that, you still won't be able to hear anymore because it will it will just burst your eardrum. All right? Oh, please don't quote me if you want to go and try. Okay? You tried before? Okay. But it depends on how close you are. So, of course, they have a device to measure. Point is, even though you may be beside the runway, the wave that hits you may be slightly less than 120. But if an exactly 120 decibel sound smash at your eardrum, then it will definitely blow it. Okay? Of course, you can then surgically repair it depending on the damage. Now, so what we have covered are the basics. Sound is a perception. No one is around. I mean, not counting animals and insects. No one is around. It's not there. But there can be vibrations of air. Next, when we look at these vibrations, we see it in the form of its amplitude and its frequency. But as a sound, as a perception, we can experience it in terms of whether it's loud and whether it's high pitch, whether it's sharp or not. Lastly, there is a limit. We cannot be exposed to too noisy kind of sounds. It's not like the eye, you can shut it and then you're safe. No, for loud noise, it will still damage you. Some people have learned how to reduce the amount of air volume inside the ear, thus reducing the air pressure. Okay, you have something called the Eustachian tube, which is actually it's not even a vessel. It's literally a tube that runs between the middle part of your ear. All right, the middle part of your ear all the way down to the back of your nose. So this is an empty column. It's supposed to be unblocked by your mucus in the nose. So that's why when you have a flu or you have runny nose, the hearing sounds a bit weird. Because when this tube is clear, the air pressure on the outer ear will be balanced by the air pressure on the inside. So even though this portion vibrates, the air pressure is the same, so the vibration is normal and you hear things as per how you hear it. But once there's blockage, and if air should escape from this, and then they are not filled back enough, so you find that the eardrum cannot move easily. All right? Or if it moves, it doesn't move with enough amplitude, so the noise is much reduced. So it is true that some people have trained themselves to use their muscles right around this eustachian tube and squeeze the tube. Okay? But I'm not sure whether you need some genetic like tongue. People who can roll their tongue is because they have a particular gene code that can allow them to control the tongue muscles properly. All right, so this part I'm not sure whether it's controlled by the genes first, then followed by your training. Okay. So to prevent hearing loss, there is not only ear guard. Some people are able to do this by reducing the pressure, but that only means that they can maybe 120 decibels hit them, right? What they will do is once they ease off the air column here, this eardrum won't vibrate that much. So maybe they are experiencing only 100 decibels. Not enough to fully burst it, but it probably will still damage it to a certain extent. But in this case, you find that maybe surgery is still can be applied to help the person save their hearing. Okay, now I don't need you to memorize this. Now I will also answer the motion sickness from just now. If you look at the ear, it's actually a multiple organ thing. First of all, the hearing is helped by channeling sound waves from the outer ear. All right, so it's a funnel shape because bigger surface area will allow you to capture more vibrating air, and then it's concentrated along this thin tube towards the inside to shake the eardrum. The middle ear consists of only 3 bones. I mean, there's a cavity here, an empty space, plus, of course, there'll be blood supply, but the blood won't flow inside here. It flows along the tissue, within the tissue itself, so it doesn't flood this place. So that leaves what? That leaves these 3 pieces of bones. They are the smallest bones in your body, and they will vibrate according to how the eardrum moves. So they will chant now. So now the air column shakes the eardrum, then it converts into now like drumming effect. Solid sound travels faster. This part here, the sound travels like normal, 300 meters per second, something like that. But over here, it can travel up to between 2,000 to 5,000 meters per second. So there's a faster conduction speed towards the inside without losing too much energy. So you get sound clarity. Okay, then this is the part that we hear. So this nail-like thing is the hearing organ. This is like your retinal cells. And then there will be optic nerve that transmit the signal back. But I want you to also take a look at here. These 3 rings, they are now in real life, right, we have the X, Y, and Z axis, which is like that, right? 90 degrees to each, perpendicular. But these 3 rings up there, the semicircular canals, they are arranged so that it's not 90 degrees perpendicular. They are actually 120 degrees apart. But they also act as the XYZ axis. What they do is when you actually, so there's fluid inside here, okay, inside this tubing. If I were to turn my head this way, it's probably going to press on one of the ring and ease off another ring. So even if I close my eyes, I will know that I have now tilted. And of course, I will have other feedback like from stretched muscles here, from compressed joints here. But minus of all these other so-called sight feelings, I will feel the pressure, but the pressure is not felt in your ear. It's transmitted and your brain calculates it and tells you your head orientation. It hasn't calculated your body. Of course, combined with your body, you will have balance. So previously you learned which part of the brain coordinates balance? The what? Cerebellum. So cerebellum will have to rely a lot of information from this portion. First thing is there is something called the vestibular system. It's not, you haven't learned where that part is, but that part will deal with the entirety of balance. The cerebellum fine-tunes that balance, and they work because they get information from your semicircular canals plus your joints, your muscle feedback, so you are able to maintain your posture, your balance, even as you run. So the inner ear is really a 2-in-1 organ. It deals with vestibular senses and perception, VESTIBULAR. That stands for balance. Okay? And it's also for hearing. The auditory nerve doesn't just send back signals of hearing or sound. It also transmits balance signals. So it's a 2-in-1 thing. When people didn't know last time, they thought that this is just for hearing. So it's stuck with the name auditory nerve. Okay? Now, okay, a few things from here. You have, the ear has 3 parts: outer, middle, inner. The smallest bones will be these 3. I don't need you to remember the name. Out of curiosity and interest, maybe you want to remember it. Down here, right, we are now switching mainly to its English names, but some books will still list its Latin name. So that's why it's bracketed here. Okay, now let's watch a quick video, then we will have sum up all these things. And this video is a friendly video. I haven't turned it on. I think so. I haven't turned it on. Oh, good. Wait.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates 3 tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea.
Okay, what is not shown here is that there are actually even tinier something that maintains the structure. So there are actually fine lines connecting all these hair cells. Okay, so if one hair cell moves, it will pull the others along. So they work in a concerted effort. Otherwise, right, this is actually one neuron cell. So if one works and then the other not work, it's going to be very tiring. Okay, so they have certain structures, we call it a filament, and it connects so they all work in concerted effort. But the fact that they are all spaced out means that they can receive different signals. Okay, all right.
Ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cell.
You've already learned this. What is this process called? Action potential, right? Okay, so action potentials are set off. So then this is actually what is sent along your auditory nerve back to the brain's auditory cortex for processing.
Cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute.
Okay, it says at the base of this cochlea, right? Keep in mind, I will show you something else shortly, something in more detail.
The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Okay, finish recap already. And bring it back and yay. Okay, now this is how small, how tiny that 3 small bones look like, all right, on the fingertip. So these are the 3 areas. Notice, I don't need you to memorize all the structures. Like I said, we're not doing about the physiology of hearing, okay? So this is just, we're going to tie it to behavior soon. And if you want to experience all this, you can try it. I'm not sure whether this is updated or not, because it's just a fun website. I didn't check, okay? But let me not spoil the thing. You can follow it. Just make sure that you have headphones or earphones on, okay, when you do this, all right? Now, let's focus on how we can, like for vision, we know that color is important and there are several mechanisms for it, right? So for frequency, this is a very important thing for us because notice that even as I talk, the pitch varies. So it allows us to transmit not only the content of the informational content, but smooth. For example, if I am about to drown in water and I shout, help me, please help me, I'm going to die. Will you come and rescue me? Okay, so I got to vary it. Otherwise, it will not stir you into motion, right? Keep that in mind also. We'll go to that shortly. First, let's understand the basic mechanism for pitch. Loudness is simple. It's just this one. I don't need to explain much. All right. So everyone can usually understand this. Pitch is tricky. The so-called sharpness that you hear, it's actually not a single one sharpness kind of thing. What do I mean? Because your ear, your brain, auditory nerve, they cannot withstand, like they are not able to fire at 20,000 times a second. Your neurons they fire at 1,000 times a second. It's already hitting the max. You go push a bit beyond, right? They'll probably last a few minutes and they'll die. So how is it that we can actually detect something so high in frequency, 20,000, when the neurons itself can only fire up to 1,000 times a second? That means sending action potential at 1,000 electrical impulses a second. Now the answer is simple. Remember just now, the fella tells you that, where's the picture? This thing at the base, which is here, right? And the tip, it detects different frequency. Because the hair cells, the cilia cells, they have evolved with different flexibility. The cilia cells located nearer to this place, they detect higher frequency.
What about people who are tone deaf, a defect in the ear?
Okay, I'll answer that shortly. Let's finish with the basic mechanism first, okay? So I'll repeat that question to the rest of you here, and then we'll talk about it. So we have two pending questions. One is motion sickness, the other is the tone deaf thing. Now, from normal functioning ear, this part is actually high, can detect high frequency, meaning remember just now I said there are very fine line, like very thread-like structures connecting the bundle together, so they sway. So the bundle right nearer the base is actually very tight. It's like rubber band, you pull it very tightly. So meaning it's already very worn up tightly, there's not much room for damage. And at the same time, a bit of swaying from it. Now, even though it fires at 1,000, the brain knows that it is a signal from this location. So it will now interpret this must be high pitch. So it gives you the experience, the perception that, it's a high pitch sound. On the other hand, as you run the hair cells along the inside of this snail-like thing, up to here, it will only detect like a very low pitch. But the truth is, the pitch is only detected somewhere between about 100, not from 20, it's actually from about 100 all the way up to about 20,000 along this. So as it rolls about 100, it will start to move until it's over here. This small part is 20,000. So then you ask, then how about the 20 hertz to 100 hertz? Now, these structures are not just microphones. They have a different way of behaving too. When a very, very low pitch sound comes in, right, it will cause ripples along the fluid inside, but the ripple is felt so slowly. Then, right, and it will hit all these cilia cells in a very light touch manner. So all of them will start to sway a little bit. Instead of some, right, when they are more tense up, they react to the high pitch energy and they swing more. So now when all of them are swinging very little bit, the brain that interprets everyone is swinging. So that means it's a super low pitch below 100. And the slower everyone is swinging roughly at the same timing, the more the brain will interpret it closer to 20 hertz. Otherwise, it will think that it's closer to the 100 hertz. So what does that mean? Now if we go to here, so what you have is actually the part where different locations on the cochlea gives you different pitch sounds is actually the place principle of how we experience sharpness of sound. But this mechanism has a very big drawback. First of all, right, notice I mentioned by about age 30, you will probably only be able to hear 15,000 hertz. The reason, most of the time, right, not all the time, but most of the time is because this is the part is where the three bones, the hammer, anvil, and stirrup will hit. Then it's not shown here. Look at this. This is called round window. Okay, there is actually an oval window. So this cochlear structure is actually quite hard. It's like a bone itself, but hollow. Then, right at the connecting points between this stapes and the cochlea, this connecting point is actually a very soft membrane thing again. This is called the oval window. Now, if this is hard, so if this is hard, it doesn't move. You smack at it, no sound will go. Not much sound will go through. But if this is able to vibrate and push at the fluid below, so as it smash, this thing goes in and smack the fluid inside. Smack, smack. The fluid vibrates. Then you will have what? Your fluid will ripple. So you capture the sound. But this is also at the point of impact. So notice this side, when it's already very tight, is prone to damaging, just like a rubber band. You pull it tightly, you snap it, it could just break. But when the rubber band is not pulled tightly, you dong dong dong, it doesn't break. So the cells here are prone to dying. Give it 2 decades, 3 decades, they are probably gone. So you don't hear it anymore. So you are unable to detect 20,000 hertz. Okay? So if you still can, all right, then go sayang your ear. Now those of you who are still young, don't damage your ear. All right? Luckily, we don't really rely on 20,000 hertz all the time. In fact, vocal cords production of frequency is mostly between about 2,000 to 1,000 to about 4,000 hertz. Okay? But in emergency, we have an extra range for ourselves. That's how we evolve. So notice that when this part is gone, the brain thinks that it's okay. So we never actually evolve any mechanism to make sure that the 20,000 hertz lasts for life. All right? Now, then the other part is what happens when they all swing at the same time. That's when you have frequency principle for the very low pitch. So we have what? We have every location sensitive to different pitch, but once that part breaks down, you lose. The disadvantage is you lose the ability to hear that range. Okay? And the higher pitch usually go first. This part is when what? The nerves evolve another way to capture another range. Remember, you only need about 1,000 to 4,000 most of the time. All the other two ends, they are for emergency use. So it evolved another mechanism where everyone swings a little bit and it interprets it as low frequency. Which gives us what? This is the most complex form, and we still don't fully understand how it really works. But what we have noticed is this. The cells, although they don't really have a brain because they are just cells, they have the cells, right, like I said, they don't have a brain, but they have some kind of way to communicate and work together. For example, if they swing very quickly, they are prone to damaging, right? So if your sound is like 4,000 hertz all the time, they will swing like mad. They will die soon. In order not to do that, you find that they also capture various clusters to work in this way. Imagine this, 2 clusters, so it's easier. When they are swinging like this, in concerted effort, now let me give you some timing. 1 second, 2 seconds. That's how many hertz? 2 hertz, because I swing to and fro and back every 1 second. Now, if it becomes like this, okay, 1 second, 2 seconds, what is really happening is this part will swing one, this part will swing one, but they are half a beat off, correct? So somewhere in the brain, it will then analyze this. It will say that, so you are firing at the same frequency, but both of you are half a beat apart. So if you sum up, right, that means half a second, one beat is actually completed. So in 1 second, 2 beats are actually being produced. Okay, if the mathematics don't get to you, never mind. Just know that when they swing half a second apart, it multiplies back to 1 second, it's two beats. Okay, so now, right, if you are trying to produce 1,000 kind of waves, they only need to swing 500 if 2 clusters are involved. And if 4 clusters are involved, do they even need 500? Then they are just 250 each, right? So moral of the story is, if they swing like a quarter of a second apart, they will split the load, work together, and still give you the correct experience. That's how they maintain their lifespan. They don't work that hard. They know how to take breaks. They know how to split the load. So volley principle is when all the different combinations, right? So they have place, they have frequency, and they also swing in synchrony just to give you the correct pitch. This was a very debatable thing. When it first came out, almost nobody believed it. They were like, sure or not, show me more evidence. How could this happen? So eventually, the community actually realized that, yeah, it's true. All the testing show that there is something like that. They really swing a bit off beat, all right? But we still don't know how they are able to do that, and then why the brain can know which part is swinging and knows how to interpret correctly. Okay? So in other words, understanding pitch, we have a simple where it's located, where the string is located. Are they all swinging at the same time but very slowly? Or we engage different clusters and have them swing in synchrony but maybe half a beat apart, or maybe a fraction of a second apart, and then we combine the signals to know what's happening. Okay? Now, this usually activates in the middle range, somewhere around 1,000 to 4,000 hertz. You find that a lot of the volley principle of activating hearing is engaged. Okay, but that makes sense because why? This is our most common range at talking. Doesn't matter what language, it's usually this particular range of frequency. So we have something that not only works smart, but it doesn't spoil easily. Okay. Now that you know this, the rest will tell you about what? For example, tone deaf. Tone deaf comes in 2 forms. One, the location on the cochlea is not well coded. So these people, they don't capture the sounds, but this is a very low chances of occurring. The higher one is that the person has some difficulty translating the signal. So although the wave it's there, the signal is sent to the brain, but the brain cannot learn how to identify it properly. So it's more likely a problem that arises at the auditory cortex all the way into the temporal lobe. Okay? And this I'm explaining because of that question just now. Someone online was asking, what about tone deaf people? Fortunately, because it is a brain problem more than it's an ear problem, so it can be reduced through training. So people who are tone deaf, right, if they actually try to identify sounds, there is a limit. It doesn't mean that they can do it like suddenly go into musicians level. Okay? But for general sounds between 1,000 to 4,000, because we can engage multiple mechanisms, so consistent exposure to the sound and getting feedback, what is this sound? Then after that, right, try to guess at the tone. Once, twice, doing this for 1-2 weeks probably won't help. But if the person persists and trains every day for about 15-20 minutes, up to about 6 months to a year, the tone deaf part will significantly reduce. Okay? It doesn't apply to everyone. Some people, they really have a problem in the the primary auditory cortex. So it still depends on the part of the brain that's blocked. So if it's those basic portions, then it's tough to help them. All right. So remember last time when I showed you the temporal lobe, I said that the hearing part of the brain, it comes in concentric rings. So I said if you read and if they draw in concentric rings, don't be confused, because that's how it's supposed to be like. The auditory cortex is not like one spot there. There are parts of it that analyzes basic sounds like pitch and amplitude, or loudness and pitch and loudness. And then as it goes wider and wider to the outside ring, it pieces together the information and gives you the melodious experience. So the further it goes out as a problem, the easier it is to retrain. Okay.
There's someone asking about vertigo as well.
Okay, vertigo is combined with the motion sickness. Hang on, we are reaching there. Now, this slide, I think that's about it. It's only meant for your information. So some people want to ask, oh, what about nowadays they read that there are ways to help people hear things by putting implants. It can be done if let's say, right, we realize that the people's nerve and brains are intact, but the hearing, all right, is already damaged. As in just now you see the ear components are damaged. We can actually implant what? So we have a microchip implanted underneath the skin, usually in the shoulder. This is connected to a microphone, all right? And then at the end, then from the microchip, right, another wire is directly inserted either into the auditory nerve, okay, no, not either, it's into the auditory nerve, so that it will send an electrical impulses, meaning the microphone, right, is something that's still external. So they may actually hook it on the ear, or it's a very tiny one hidden inside. It receives the signal, then the microchip processes the signal, sends the electric current, and the electric current directly jolts at the auditory nerve, and then it goes into the auditory cortex. But it's not good for everyone. Why? Success rate of the surgery is not very high. So basically, there is a high chance, about 60–70% chance, that during the surgery, the auditory nerve can be further damaged by surgical instruments, or maybe the surgeon's erroneous movement. So this is like, unless maybe the person is still very young, has many more years of quality life ahead, and really needs to opt for want to hear again. Okay, then this thing. So that's cochlear, all the implants. All right. Now, later on, actually, there's one part about the motion sickness part. I split it up this time around, but we'll come to that later on. Now, before we move on, okay, so two questions, right? What was that one?
There's vertigo and motion sickness.
Okay.
Yeah.
Now, before we move on, I'm going to now let you watch that video again. As you watch, then I like you to write down your insights again, plus then we will debunk some myths. Little noisy. This is still not the original soundtrack, of course, because you're supposed to hear like machine guns and stuff, right? Replaced it with the help of Kiko with another piece of music. Now, with this new added information, write down your insights, your feelings, or whatever you've gotten watching this video again. Let's quickly do this for 3 minutes. On Nero. yeah. 2 steps from hell. Okay, in case you are as curious as Rachel, the piece is called Nero by 2 Steps from Hell. That's the music. Nero is Nero. That's the name of the music. Okay, good. Thank you. No, I'll eat later. I thought you are supposed to man here and downstairs. I was.
I'm not, it's not possible to do.
Yeah. So Karen was asking me just now, like last week. Was it?
It was just you, right?
Yeah. No, was Kim downstairs when you?
But I think Kim left before.
Okay. I see.
That's why I was shocked.
I thought you all left together.
No, I cannot remember. I don't think so.
Oh, I got it. Okay.
Then I'm asking her, why are you here?
I see. Okay, 1 minute left.
Mr. Lam, no sounds. Mr. Lam, no sound.
Hi, Mr. Lam. We are not able to hear you.
Right? Done? Oh, I can hear myself. Doesn't sound so good. Now I know what's been disturbing you all this time. Maybe that's why you're jammed, you see. You've listened for 2 hours and 2 hours plus, but then the clip only 6 minutes, 3 minutes, 3 plus 3 is 7 minutes max. Ah, the trauma. Done? Okay. There are all these delays, no good. Okay, now, I think online people, you should be able to hear me now, right? Okay, so you didn't miss much. I was actually asking around when you rewatch the video with the music. This music is not the actual soundtrack, because the actual soundtrack will be, of course, robotic sounds, machine gun firing, but I replaced it with a piece of music. Just now I asked them, did anyone feel some kind of goosebump? Because some people, when they listen to music, they have certain pieces, not all, they have goosebumps. Now, we didn't have anyone with goosebumps here. Some people have. Oh, okay, we have one person with goosebumps. But we do have a few that say that no, there's a kind of different feeling when you rewatch the video with sounds. All right, and we didn't stretch this out. You are under tight pressure. If we have done this in a more relaxing way, maybe there's more. But so far we have at least one person saying that there are more things to write now after watching it with the music. What was something extra that you added?
I guess the music made me look deeper into the robot's emotions, I think.
Now, this is actually something very important. She mentioned that the music actually made me look deeper into the robot's emotions. In other words, right, music, can it invoke emotions and feelings in us? Well, this one we know. You don't need any scientific research to tell you that, even though there are also evidence to show this. Now, let's push this a bit. Do you think music can make people more creative? Yes, too. The question is how, right? Because there's no point knowing this and not knowing how to use it. And the last thing that I'd like to check with you is, have you heard before people keep telling you, the language brain is on the left side, the music brain is on the right side of your brain. And there are even programs that try to stimulate the right side of your brain so that you are more musically inclined. Okay? Now, should anyone be buying these kind of programs? Let's say they really want to, kickstart their musical career. Should they buy this kind of program? Why not? After all, you have the right side and it's tied to emotions, and then you become a maestro. But you're saying no, is it because you know Mr. Lam? Better say no, this is not a trick question. I think that's what she means. Okay. I'd like you all to watch a video before I answer all these things. I think then we have to switch to that YouTube thing. Can we? I think online people should be able to see because they are on that screen, but we need to project here, right?
Hold on.
Oh, I can share screen? Okay, I don't touch, you do. I don't know, later I spoil it.
Regain language.
For the people here, right, if you don't get to watch this, copy this down.
It should project on, but it's not.
Because I think the online people should be able to see. But if you can't, go and watch this. It's on YouTube. So you go YouTube and then you put in this keyword, it should come out. How does music affect your brain? There's one more word, what wired tech or hard tech or something like that. Tech effects, is it?
Sometimes I compare it to.
Okay, so we need to drag this to there.
Drag to there. Oh, okay.
Really not.
We bring it back. Then I have to minimize the window though.
Okay. This is my screen now.
Can, no problem. I drag this. Can't see. This whole thing, is it?
This whole screen thing is my screen. So I don't know whether I can drag my screen.
No, I can't.
So I stop share.
The other way is I zoom and I
send you the link that you can open
Okay.
your chat.
Alternatively, if you want to use a cell phone now, you can. How does music affect your brain? You go fast forward to the part 11 minutes and 9 minutes and 4 seconds. Okay, if you are using your cell phone. So this is what you key in into YouTube. Yeah. So the publisher should be Tech Effects. I remember a tech word. You only need to watch from 9:04 to about 11 minutes 06. Oh, we are seeing all of them. We need to
Laura's job is
minimize
to help
this and
patients
then we can push it over. There. Yeah, now we drag it to that side. There, it's over. Now we can play. Then you enlarge it. Yep, it's on. You turn on the sound.
Okay, let me check if it's online.
Okay, now, what you're gonna, there are several pieces of information. Those of you online people can hear me, right? So we have the video on. Now I fast forwarded to almost near the end. At this point, right, so I'll give you some background. They are looking at this is research on how music affects the brain, but it's given in a nutshell, so it's good for this kind of introductory classes. Rather than I cite off all the various research literature for you. Now, we're going to look at creativity and music's impact on creativity, what it actually is. And then we are going to resolve the question, what language is on the left, music is on the right. Should we buy this kind of programs? Because technically they form part of your sensation and perception, right? Because like, for example, if you can only appreciate music with your right brain, then of course if you want to be musically inclined, it makes sense to stimulate this portion, so it raises your ability at perception. All right? Okay.
Learning to play music can help strengthen brain connections. But what about making music?
To me, music is like it's the language of humanity.
Can you hear?
No matter where I go in the world, if I'm playing something, it doesn't matter if someone can't speak the language.
Can I?
This is Xavier de Frapoulis, better known as Fantastic Negrito.
Oh, he introduces
At
him.
UCSF, Charles Lim, a neuroscientist who studies musical creativity.
Yeah.
The Duffer's up next.
To understand how Fantastic Negrito's brain works when he's making music, Dr. Lim had him play one of his songs while going through the fMRI. So how did his brain respond? The areas that process sensory and motor skills, along with sounds, lit up. You can see them here, red and yellow. Makes sense, right? Here's the really interesting part. We then asked him to improvise to see what happens when he created something totally original.
So he started rapping. This is original.
Now watch what happens to his brain. Well, the areas that were active before, the ones that deal with motor skills and sounds, are even more active. See how there's way more blue in the front of his brain? That's the prefrontal cortex.
Okay, don't get it wrong. If you notice, if we turn back, right, you will see, maybe I can do this 5 seconds only. Watch the red color areas on this side compared to the red color areas. Ignore the blue for the moment, all right? Maybe we can see it like this. Yeah. So it's clearer. Now look at the red. Do you see a more intense red on the left side or a more intense red on the right side? Ignore the blue. It's going to be difficult because the blue is going to get in the way. Okay? Let's look at the area. Now, okay, let's look at this yellow spot. I think it'll be clearer. Red is more intense than yellow. So this yellow, which one is bigger? Left side or right side? Left side is bigger, right? That means the right side is actually more activated, correct? So there's more red than more red here than the other side. Okay, then let's look at the blue one. So blue, we have a lot more, but let's look at the front part. So this was, I wanted this nice clip, but okay. Obviously, you can tell which side has more blue, correct? But just to let you know, blue means that that part of the brain is now having less activity. It is not activated. So the prefrontal cortex is less activated when the person is improvising and creating something. Got it? Now, first of all, right, let's look at just consider the red part. Online people, I think you can hear, right? If you want to chip in, you also can. For the red parts, did it only occur on the right side of the brain? It's everywhere, isn't it? Actually, this picture is because they are only doing this study. All our studies show that when you listen to music, various parts of your brains will light up. Where it deals with memory, deals with emotions, deals with motor movements, so your movement, and then your ability to concentrate on things. So basically, various parts of our brain light up. But if we slow down and we show you, or we let you experience certain types of music, of course, the lighting up will be in different ways. But in real life, we don't only listen to one music or one tone. So if we keep changing this or listen to several pieces of music or songs, then what is likely to happen is that the entire brain will be more active. What does this tell us about the notion that music is in your right brain and language is in your left brain? Let's throw it out the window, right? No, so therefore we can now answer the question. If you want to become a maestro, should you buy this kind of programs that only train your right brain? Obviously not too, right? Music can stimulate your whole brain. It will make you, but the thing is, if you want to raise creativity, what must happen? So notice how much more the brain has become disinhibited. Because why I say this is, the prefrontal cortex, last time you learned about prefrontal cortex is meant to do what? Some big term. Executive function. All right? Executive function is equals to what? There's planning, there's anticipation. But think about it. When you are planning, right, will you act? If you plan to eat a burger, will you be eating the burger or you're just going through the process? Going through the process, right? In other words, you are actually stopping your behavior. Okay? So you run through everything and make sure that everything is all right before you act on it. That's one part of what the front brain is doing. It's letting you go through all the action, but it won't allow you to engage it. You are stopped from doing it. But when he becomes more creative, what happens to the inhibition? Blue equals what? Lower activity, right? So what happens to the inhibition? It reduces. So reducing certain types of frontal brain activity allows you to become more creative. Here, he starts it himself because he's trained to be creative. What about the rest of us? How do we train ourselves in doing so? What if you start to engage in more karaoke singing? That's part one. What if you also sing during your shower time? Now, what happens when you are, let's say you're at work, and then you face a bump? You cannot, there's like, you need a solution. This is not like an emergency, okay? So maybe your boss tasks you to do something. Will you be sitting at the office desk, mulling until what, 10 p.m., doing overtime? Or maybe you could try singing and thinking about it while you take your shower. Which one will have a higher likelihood of making it work? Depends. If your work requires you to do plenty of calculation, you may have to still sit at the office desk, do the calculation first. Then keep the figures in mind, because now you need to play around with the figures. When it's time to play around with the figures, go into the relaxing mode. In the shower, you sing a bit to get yourself moving. Then you think of the thing as you sing to your favorite tune. Now, you don't sing something difficult, then you're basically blocked. Because now you have to recall like memory, the other side, right? Recall and jam, and then you cannot be creative. So you got to be singing something you like as you think. Initially, it's going to be tough, so you find performance will drop. Why? Because people are not used to thinking deeply and singing at the same time. We are not full-time singers. But on the other hand, if you do this a few times, so you don't wait until your boss gives you a task. Whenever you're doing something, when you watch shows, when you do something and then you recap about the show, you do it while you're singing. So you are now automaticized, you're used to it. Anytime you want to sing and think, you can. So unlocking creativity has many ways. This is one of those ways. And it is what? It is using something that we can perceive and come into what? Appreciation very easily. Music. Go think about it. This is, of course, just an introductory course. I cannot tell you the step 1 do what, step 2 do what. Okay, go home, practice, then come back and see me in the next session. I can't. But I'm giving you some steps for you to go and explore and also reach automaticity. Then, so that when you use it, it's easier. Okay? For those people who don't get goosebumps or whatever, one other way out is what? Listen to music that you like first. But music need not be classical. It can also be song like the jazz you hear that fella playing. As long as it is not white noise, it is not, if you enjoy heavy metal and you can somehow, right, or gothic music, but you are able to derive some rhythm from it, that's okay. But for sounds that you cannot derive a rhythm, or it's just pure white noise, and then those are disruptive. So that's why there's also research since 95 showing that people actually, when they expose themselves to like Mozart music, over a period of time, usually a few months, they actually clock 10 points increase in their IQ. Okay, so potentially more intelligent. All these are unlocked by reaching out to the correct type of music. So I say it need not be Mozart music, it's something that is rhythmic for you. Even heavy metal, provided you can derive rhythm from it. Okay, I know you're tired. So the last part will be the motion sickness. Motion sickness occurs because when people when they are going through some vehicle or some moving platform, the brain registers movement, but you are so anxious, you insist on being stable, you don't want to go with the flow. So you are actually blocking the proper signaling. Because for example, the signaling says go left because you're tilting, then you say, no, I gotta sit straight. You fight this a few times, then the brain goes disoriented, it becomes motion sickness. Usually it starts with anxiety about movement. And what was the other question? Vertigo is a fainting spell, but then there are many causes for this. I don't think I can answer this very quickly. For one type that can answer here is, remember your semicircular canals? One type of fainting spells is because, or the world becomes disoriented, is turning, It's because some people, they got blood clots broken off somewhere. Maybe some capillaries got stuck. And this blood clot flows into that semicircular canal and add extra pressure to the fluid inside. So if I tilt this way and you give me extra pressure, I'm going to feel like, oh, I'm going to fall. So when they straighten, and then this blood clot sometimes may move around and hit, so I will feel like my world is spinning. All right? So this is one type of vertigo, but it can actually be resolved usually by seeing, the usual GP won't be able to help. All right, a neurologist or a physiotherapist trained in certain maneuvering, and they make the person go lie and then come up quickly, and turn a bit, and it will move the blood clot out of the semicircular canal, and then they won't have the problem anymore. Beyond that, it has to be medication. But then it's a long topic lah. So I will just stop at where this thing can go. Okay. All right. I see you all next week. Welcome.
Thank you. Bye.
Mr. Lam.